and record. So this is the exercise that we did on page 11 pertaining to section 7.2. We use the p-value. We're trying to redo this exercise using critical value methods. HO, guys, doesn't change. It's the same thing. Doesn't matter what method you use, you still have to state the null in the alternative hypothesis. You have n is 25. You have x bar, which is 20,695. And you have sigma is 2250. And you have alpha to be 0.05. The next step, guys, is to calculate the test statistic, which is this. That's the test statistic. You use your calculator. We did the z-test to find the test statistic, but if you do it by hand, it will be x bar, guys, is 20,695 minus the mean. This is the value in the null hypothesis, divided by sigma, which is 2250, over square root of n, which is square root of 25. And if you guys do the math, definitely the answer is going to be exactly this, negative 1.79. So far, step 1, step 2 are exactly the same. The next step is, which is different from the p-value, is the critical value method. And let me explain it to you guys. This is Z. Okay. Can someone tell me whether this is a left tail test, a right tail test, or a two-tail test?
Two-tail test.
Two-tail test. You agree because it has a different from sign. Okay. If it is a two-tail test, look what you do, guys. Shade two regions here. And those regions are called the rejection regions. And this is called the rejection region of HO. And the region here, it's a non-rejection. This is where you accept HO. If you have a left tail test, guys, you shade an area to the left and call it the rejection region. If you have a right tail test, you will shade an area to the right and call it a rejection region. And if you have a two-tail test, you will shade two areas on the left, on the right, and calling rejection region. Now, there is a value here, guys, and you agree with me, they're symmetric, so it must be the same value. If this is a positive, this one will be negative. And I'm going to show you, this is called the critical value, and you learned how to do it when you did confidence interval. It's exactly the same way as we did confidence intervals. Does anyone remember? So alpha, when we did a 95% confidence interval, guys, do you still remember how we found those two critical values? What did we do? Which is, we're going to review today. We had 100% minus 95%, which is 5%. And then we divided by 2 because we have to split up, you know, the 5% on both sides. And we did an inverse norm on 0.025. And actually, I asked you to try to memorize those values. For 95%, it's 1.96. For 90%, it's 1.645. And for 99%, it's 2.575. And guys, when you have a two-tail test and you have a 5% level of significance, the critical value is exactly the same as the 95% confidence interval. So it will be 1.96. But I'm going to do it. So if you do inverse norm here, and just alpha is 5% divided by 2. That's it. That's all you have to do. So why we're dividing by 2? Because we have two rejection regions. So it would be 0.025, comma 0, comma 1. If I go to my calculator, guys, and show you how to do the math here, the critical value.
Question. So you divided alpha into 2?
Yes. So you don't worry about
Okay.
confidence interval. I'm showing you that the 5% with 2 tails means 95% confidence interval. But if you have 2 tails, you just take that alpha and divide it by 2. If you don't have 2 tails, you just put it as is, which I'm going to demonstrate another example later. So you do inverse norm. You still remember, guys, how to access the inverse norm? You go to second and distribute. Inverse norm, 0.025. And guys, don't be surprised. You should get 1.96 or negative 1.96. There you go, negative 1.96. So this one, guys, is 1.96, and this one is a negative 1.96. And let me show you how to make a decision to reject HO or fail to reject HO based on the critical value. What is the test statistics from number 2, guys? It's negative 1.79. Put it here on the number line. Where do you think, guys, negative 1.79 will be? This is 0 in the center. Would it be after negative 1.96 or to the left of negative 1.96? Where would that be? Negative 1.79.
To the right of it?
Yeah. And this is a non-rejection region. So it ended up in the non-rejection region. So you failed to reject the null hypothesis. And look, how did we do that last time? Watch. Failed to reject the null hypothesis. So if your test statistic ends up in the non-rejection region, you fail to reject the null hypothesis. If it turns out in the shaded regions here, you reject the null hypothesis. And this is what we call the critical value method. So false in non-rejection region. So we don't use p-value here. So we fail to reject HO. Let's say this one, oh, negative 9.76, sorry, 79. Let's say this was negative 2.11. The negative 2.1 would have been right here, guys, and then you reject HO. So when you use the p-value method, you compare a p-value with alpha. When you use the critical value method, you compare the step number 2 with the critical value that you find using inverse norm. You number with a number and a p-value with alpha. And then step number 5, guys, is exactly the same thing. So this is what we call the critical value approach. Now I'm going to go to another exercise that we did earlier together and show you how.
Really quickly, I'm so sorry. Can you,
Yeah.
How is it that we determine if it's a two-tailed test again?
Oh, because not equal to.
Okay, thank you.
If it is not equal, it's a two-tailed test. Otherwise, it's a one-tailed test. So let me go to one-tailed test, the problem that we did earlier, guys, and show you. Okay, this one. I'll show you how to use the critical value approach here. So step number 1, guys, no change. It will remain the same. Critical value method. Step number 1 is exactly a fast food outlet claims that the mean wait time is less than 3.5 minutes. A random sample of 15 customers has a mean of 3.4 minutes with a standard deviation of 0.6. That's S. So you know, guys, we did a t-test here. If alpha equals 5%, test the fast food outlet's claim. Assume that the population is normally distribution, use TI-84. So we're going to do the critical value method. So HO and HA, guys, do not change, remain the same. We have N is 15. We have X bar to be 3.4. We have S to be 0.6. And we have alpha to be 0.05. The next step is to find the test statistic T, which has this formula, guys. You could still run the t-test and find t using the t-test, but to do it by hand, it will be 3.4 minus the mean, which is 3.5, divided by s, which is 0.6 over square root of n, which is 15. And we've done it using the calculator already, guys. I have it, negative 0.646. Now, let me show you guys how to find the critical value. First of all, is this a one-tail or two-tail test?
A one tail?
One tail. To the left or to the right?
To the left.
To the
To the
left.
left. And look. So you shade this. This is a rejection region of HO. And this is the non-rejection region. All I need, guys, to find this number here that splits up the rejection region from the non-rejection region. And this is called the critical value. We did it in chapter 6. Okay. Alpha is 5% here. And this rejection region has this area of alpha equals 0.05. You cannot do inverse norm here, guys, because we're doing a t here. So it's called an inverse t. Or, guys, you can simply use table 5 that. Let me just get the table and show you guys how you could use this table. That's table 5. Look how easy it is to use the table for the critical value. Forget about chapter 6, level of confidence. We don't care about this. You see what it says here? One tail or two tails. What do we have in this exercise? One tail or two tails? One tail. What's alpha? 0.05, correct? Okay, and what's the degrees of freedom? What's the sample size? Let me show you the sample size. 15, so what would be the degrees of freedom here? 14, n minus 1. Okay, 0.05, guys. So look, the first row is dedicated for chapter 6, and the second row and the third row dedicated for chapter 7. So 0.05, and I need 14. So I'm gonna go down to 14 right here, and I got a 1.761. Okay. But since this is a left tail test, guys, it has to be negative. So I'll put negative 1.761. So we do this. Now, what was the test statistic, guys? Negative 0.646. Where do you think negative 0.646 is going to be? To the right of negative 1.761 or to the left? How would you place this on the number line? Do you guys agree with me that it should be somewhere here? So it's not in the rejection region. If it's not in the rejection region, what's the decision? Not in the rejection region. So the decision will be what? Fail to reject HO. And let me show you guys this exercise. What was it? We ended up failing to reject HO. I don't know where I put the exercise, but we end up failing to reject HO. It's the same decision whether you use the p-value or the critical value approach. The p-value compares with alpha. The critical value, it's a number with the number. So you take the number from step 2 and you compare it with a number from step 3 where you use table 5 or you use inverse norm to find the critical values. If you feel comfortable with it, you can use this method, but I think I'm planning probably 99% all of the exercises so that you can use the p-value approach in them. But I thought, just to share it with you, we will not be using it much at all, but it is a method that is available. Oh, right here. You see, guys, we end up failing to reject the null hypothesis. And if you use the critical value approach, you will fail to reject the null hypothesis. And if it is a t-test, guys, it's always easy to find the critical value using the table because look, all you need to decide whether it's one tail or two tails right here, and then find the degrees of freedom and get the number. If you have a right tail test, use the number as is. If you have a left tail test, make sure to put a negative sign next to the number, and that will be your critical value approach. All right. I'm gonna give you